And I will discuss our feature that is called semantic search, which helps users of the semantic layer explore parts of the ontology that is of interest. These ontologies can grow pretty big, especially for large enterprises. So it's useful to have this thing. And then I'll go on and discuss how to weave the data into the ontology. And the problem I will focus on is how to verify the trustworthiness of a semantic layer, which is that how to know that the results that we are getting back from such a layer is actually accurate and is containing the data that we want. The solution we provide is some sort of a drill down capability from a conceptual level to the physical level. So I will demonstrate it in a live demo if I have enough time for that. Okay, so semantic layer is essentially a set of hierarchical views that present the data in some form to the user, and such a layer allows the user to express queries in terms of business concepts, relationships that are familiar to domain experts, rather than explicitly referring to physical layer names, such as table or column names. And a semantic layer is also allowing some sort of flexibility in terms of defining the views that we can use to look at our data. There has been lots of ideas and approaches developed for creating semantics and creating models for the domain. We can categorize these as such, as you can see in the slides. So there are proposals which we call the SQL first, DBT and Malloy, for example. There is also knowledge graph-based data catalogs and data fabrics. There are also industry proposals, Legend or Morphir. Legend is by Goldman Sachs, Morphir is by Morgan Stanley. And then we can also talk about standards. So semantic web is one big standard, and SBVR is by OMG. And today I'm going to call out this note here that relational AI is actually powering any of these approaches. So it's up to you which one you want to go with. This knowledge graph management system we have is actually able to support you. So in this talk, I'm going to be using a modeling approach that is very close to the SBVR one. In fact, many of the people who are on the board of the SBVR committee have created this modeling language. This is a visual modeling language called object role modeling. It is basically giving us a visual tool set for representing ontologies, domain concepts, and relationships. There is good tool support for creating these models. In my opinion, Norma is really following this principle of do one thing but do it well, and gives us a good tool to create these domain ontologies. It also has very good support for normalization, which is especially useful when creating models and working with business users. And there is some adaptation in the industry. One big user of ORM is the European Space Agency. So let me just briefly walk you through this example ontology that I will use in my presentation. And this is basically presenting a domain where we want to keep track of some customer data, when they are billed, what they are billed for, what kind of products they have purchased, what kind of subscriptions they have. And in ORM, we can represent concepts by using these rounded rectangles, such as bill or line item, as you can see it here on the slide. And you can have relationships between them in which these concepts can play roles in. So, for example, if you look at line item and bill, between these two concepts, there is a relationship called is part of, and you can easily verbalize this relationship as, if you read it in the direction of the role order, line item is part of a bill. So, and in addition to that, I'm not going to cover, but ORM gives you a very good set of constraints that you can that you can use to supply to your domain models. On the other hand, we have our data living in the modern data stack in some physical form, and what we want our semantic layer to do for us is to make this connection between the domain concepts and the physical presentation of the data, so that we don't have to find out how exactly we should be referring to the data. We can use the concepts that are coming from the domain. However, like I said, it is still it still can be it is often very tricky to find out what parts of the domain are interesting for us. So there should be some tool that allows us to explore the ontology that we are working with. And for that, we have come up with what we call a semantic search, which is exactly doing this. It's a tool to explore the ontology of the business domain, and it provides us a vocabulary for the search queries, for the semantic search queries. And the output of this search is basically a list of precise names and concepts, relationships of interest, which are familiar to domain experts. So how does the semantic search query look like? So sticking with this example, we can just say that I am interested in exploring the ontology, the part of the ontology that has some part related to the bill concept. And then we get a result where the ontology is expanded in a way that we are presented with all the relationships that bill as a concept is playing a role at. And now we have two relationships presented for us, so we can go on and further expand this part of the ontology and use line item is part of bill relationship to navigate further and see more of the ontology without actually having to understand in detail all the rest of it. The semantic search work has been already published last year at the Models Conference, so I'm not going to go into details for that. If you're interested in this kind of work, please take a look at the paper. But it was a good feedback and validation for actually a need for this kind of tool, and we were happy to present that. Okay, so in addition to having this tool that can help us explore the ontology, of course, we need to somehow make sure that we also weave the data into the semantic layer, not just have the concepts, the conceptual model in the knowledge graph. So again, what's the motivation for having this? Having such semantic layers? One of the major motivation is, as it was called out in the keynote just a few minutes ago, there are many data silos at large international companies, managed by several teams using several different approaches. So synchronization, change propagation, and duplication is always a problem. So we would like to have all the data in a semantic layer that can provide views and manages all these or solve these synchronization and other kind of problems. So how we can weave this source data into our ontology, and for that we have these declarative rules that are, in addition to being declarative, they are also executable. So this is one nice thing about using a relational knowledge graph management system, is that we can adhere to this principle where we say model is the code, and if we follow some small number of weaving patterns, then we can ensure that when we write these rules, we can analyze these rules and figure out to what degree we have woven our data sources into the semantic layer and how much work is still to be done. So let me give you an example for such a weaving rule. And here on this slide, I called out a small fragment of the ontology that I presented earlier. So here we have a line item that charges some amount. And here in this piece of rel code, you can see that we define the value type amount. We also define a set of line item entities. And then we describe the definition of how this line item charges amount relationship should look like, and how we weave the source data into this relationship. And it's not very it's not very difficult to see that the definitions on top correspond to the concepts in the ontology, and this definition here in the middle is actually a definition for the relationship. And now here in this simple case, we can easily see the source columns that we used to create this relationship. And that's exactly what we are interested in, is to make this connection between the conceptual level and the physical layer. And if we write these kind of rules and we support this with analysis tools that can read these rules that we have defined and give us a report what sources were woven into what concepts and what relationships. So we have this weaving approach, but the problem is that still these might contain errors. So maybe someone made a mistake, wrong information was used when creating the relationship. So in order to be able to gain trust in the semantic layer, we need to have the ability to explore the ontology, which is provided by the semantic search, so the semantic search queries, and also drill down so that we are able to understand that a certain concept or relationship is populated from what data sources. So the added value of this approach is that we can rapidly explore the domain and increase trust in our semantic layer. And I would like to briefly switch to this live environment and give you a quick demo how this works. But before I jump into it, I would like to go back to the ontology. So this is our domain model, some small domain model, and what you see here is the actual console that with which you can easily interact with the relational AI knowledge graph management system. So I loaded the ontology already into this knowledge graph, and I have the data also available. So the data is also loaded, and I have defined a couple of these mentioned weaving rules, following these patterns that I mentioned for weaving, to populate the semantic layer. So again, here I have the line item, here I have the bill concept. There is this relationship, line item is part of bill, and then if I go here, line item, I can see that yes, here is this line item entity, which is basically a concept, and here I have this definition of line item is part of a bill. And then in this weaving rule, I have the actual names of the sources, so the layer is populated from these two columns. And then if I go back to my query window, I can run this first query, which is about starting from the concept line item, and I can expand one step at a time the ontology that we have. So we can see here that line item is playing a role in these four relationships. And if I want to navigate towards the bill concept, I can add one more parameter and then drill down in the ontology. And then you can see here that it's further unfolded, and we could continue this navigation and explore the parts of the ontology. And then on top of this, what we also have is these drill down queries. So now that we actually discover the concepts and relationships that we would like to use, we can now go ahead and get information about where are these relationships populated from. And here in the tooltip, I'm sorry, it's a little too small font size. You can see that this relationship is actually coming from the sales table, bill ID column, and the sales table line item ID column. So if you want to verify that this is actually populated from the right sources, then you can do it with this help. And again, this information is synthesized by reading the rules that we have written once, and then this query, this drill down query, will actually understand and presents us the data lineage for that particular relationship. So what I mean by that is that now I can go ahead and can be sure that I'm getting back here, navigating through these relationships. I'm actually getting the data I am looking for. So I can list now, for example, all the bills, the billing dates, and what line items belong to that particular bill. So yeah, that's about it. That's what I wanted to show you today. So as a summary, relational knowledge graphs by nature are well suited for implemented semantic layers. Semantic search makes it easy to scope down to the part of the ontology that we are actually interested in, and the ability to link the conceptual level to the physical level helps verifying that the semantic layer is correctly populated. So thank you so much.
We do have time for a few questions if there are any.
So I'm not sure if I'm understanding. So it looks to me like essentially you map an ontology to a relational database and you use the relationships in the ontology to understand semantic relationships. Like I guess what I'm trying to understand is how is this different from what we often do when we map a relational database to an ontology? What's the semantics of the semantic search, or is there?
So here, what we are doing is writing this mapping, but this mapping is also executable. So you load it into your semantic layer, and it doesn't need. Then the data source doesn't need to be a relational table. It can be a JSON. It can be any kind of data source that you store in the modern data stack. So in this example, I was using the tabular format data, but in principle, you can use these drill down queries to identify whatever data sources you have.
But the key, just to understand, the key thing that you're doing here is you're saying, here's an ontology, I'm mapping it to the relations that are in my structured data, and as a result, we get the ability.
Right, but the mapping is executable, so it's actually populating your semantic layer. So when you run the queries, that's not running directly in your database; it's running in the knowledge graph management system.
I mean, this should be a surprise to this community that do this, and this community does this a lot. This is just another way of accomplishing it, and sort of giving the we didn't get into it today, but the knowledge graph engine has the ability to run a variety of queries that aren't easy to run in SQL. For example, graph queries or recursive queries or other queries that would be harder to do in a SQL-only implementation. So.
Right. Thank you.
So you get kind of a virtualization of the graph?
The graph shows up as a set of materialized views inside of a system like Snowflake, for example. So the engine plugs into a Snowflake microprocessor, and you get the graph is represented as a relational database in a highly normalized form. We call graph normal form, and you can do these transformations in SQL if you like, or you can do them in a more graph-oriented reasoning language, rule language like you saw.
Michael, this is just our floor now. Right.
There's a question behind you as well.
So kind of building on that, one of the things I believe is federating relational databases is always harder than one would think it ought to be. Is that kind of handled by the creation of this semantic layer, so that if you're essentially pinging two different relational databases, it's all handled by the relational AI platform?
So yeah, you have full control in your weaving rules, what you're weaving into with what concept, and you can have multiple data sources for one single relation, and then you can report out that what are those sources. So it doesn't necessarily need to be one unique. So it can be a multitude of data sources.
So, Márton, if I can also add, so this is a federation model where the data stays in its databases and you federate across it. We don't see that as much in industry now. I think it's sort of a new mode of working where, because you have these super scalable cloud databases like Snowflake and BigQuery and so on, what we see people doing is just taking data from 1,000 or 10,000 different SQL databases and pouring it all into into Snowflake. And so there is no federation anymore. They're using, as a first cut, SQL and tools like dbt to transform and clean the data in place so that they can serve, BI tools and spreadsheets and dashboards and data apps and all from like a progressively more refined model. The issue is SQL has its limits in expressivity, as I tried to hint at earlier. And so can you use more sophisticated relational languages to express more sophisticated semantics, right? Like if you wanted to express transitive closure, you wanted to express some, connected components analysis, or between the centrality, or if you wanted to do, we saw earlier talk about simulation, or maybe doing prescriptive analytics. All of these things are just not native to SQL engines like Snowflake and BigQuery, and so by plugging into them and extending them with a stored relational language, now you can express these semantics directly there, as opposed to having to leave and go somewhere else or federate. And federation obviously has its advantages, but for it has also its limitations, right? Because you gotta, sometimes you have scalability issues with that approach. Okay.
All right, well, speaking of DBT, we do have Anna Filippo here as our next speaker in about 8 minutes, so if there's time for a quick break, or please stick around, and Mom will be here to answer questions. One more than that.
Can you bring the slide about the paper?
I should be also example by that.
I think the theme for this afternoon is different approaches to this idea of a semantic layer. So it's great to have dbt on board. I think they've brought this idea to the mainstream and are starting to think beyond just SQL being the language, right? So they've announced SQL plus Python support for expressing semantics, but obviously when you go to Python, you're now back in procedural programming land, and so maybe SQL plus Python plus a language like this. And then I think Steve is going to be talking about Morpher, which is yet another cut on this idea. So really interesting space, and I think a key to adoption of a lot of the ideas of this community in the mainstream, because so many people have so much data in systems like Snowflake, they've got to create an ontology or a data model of some kind to sit above it to make it coherent. It's just too much complexity to have every BI user go navigate 10,000 data models.
This is true. This is very true.
So, we're going to get them one way or another. So, get the ideas in somehow. So. All right.
All right, we have 5 minutes for the next speaker. Thank you so much.